All right. In this video, we're going to graph. This is for Math 230, one a day, 11, example one. So in this question, or example, we want to graph the function r of t. It's a vector valued function. So each of the components I, j, and k have a corresponding parametric function, x of t, y of t, and z of t, corresponding to the direction of the vector. X of t is given to us by cosine of t, y of t is sine of t, and z of t is equal to sine of 2t. To graph this, we're going to use GeoGebra. So I'm going to pop over to GeoGebra really quick, and we will start there. We're back here in GeoGebra, and so I have the algebra window and the 3D window open. And so to graph this one, we're going to type in the term curve. This is how we're going to parametrically plot. For each of the components, it's just like the vector. So we're going to have x of t, which is cosine of t. Y of t was sine of t, and z of t was sine of 2t. So those are components. The next part is going to be what is our parameter? That's t. Where does it start? Let's say 0. And where does it end? I like to do it this way. I'll put in the letter N here. That's going to create a slider. And I like to see how it traces it out. So to do that, I'm going to make this go from 0 to 2 pi steps of 0.1. Okay, and why is that nice? Because now I can see how the graph actually is graphed as I move my argument along. Goes as my angle goes from 2 to 2 pi. And if I don't want to sit here and graph it, I can hit the play button and watch the curve untrace in real time. And that's really cool to kind of see how the formulation of it comes out. In this example, we're going to look at the function r of t. This is example 2 for 1 a day 11. R of t is equal to 3 cosine t I hat plus 3 sine t j hat plus t squared k hat. So we have 4 things we need to do. We want to graph it. We want to find the velocity and the acceleration vectors. We want to know its speed at any time t. And then we are curious to find out if the vector or the velocity is perpendicular to the orthogonal to the acceleration vector at any time. So we're going to see if the resulting vectors are orthogonal. Okay. So to graph it, we're going to hop over to GeoGebra real quick and do that in that program, and then we'll come back and work out the remaining. So let's look here. So I have my n from the last example. This is going from 0 to 2 pi. So let's plot this curve, and we have 3 cosine t, well, big T, 3 sine t, and t squared. And t is going to go from 0 to n. Okay, and so there's our graph. And you can kind of see as n sweeps out, the path that it's tracing. And let's maybe make this go a little bit further. Let's say we make that go times 5 times that. Let's see if that'll give us a little bit. So that's a little bit further out, just to see if we can get a little bit better understanding of what it's doing. All right, so let's see. We wanted to identify, we know what r of t is. Okay, so that's given. So so we've done this. Let's find the velocity. So we know that the velocity is drt. So we're differentiating each of these terms individually. I'm going to write this in vector notation just for the sake of simplicity. The derivative of cosine of t is minus 3 sine t. The derivative of sine is 3 cosine t. And the derivative of t squared is 2t. Okay, so there is our velocity, and now our acceleration is going to be dv dt. which is also d squared r dt squared. So the derivative of this is going to be minus 3 cosine t. Derivative of that is going to be minus 3 sine t. Derivative of that will just be a constant of 2. Okay? All right, so there's our velocity and our acceleration. We next wanted to determine the speed at any time. So the speed, so we're done here. So the speed, well, the speed is just the magnitude of the velocity. So we're going to take v and dot it with v, and then take the square root, aka this is the magnitude of v squared, of v, sorry, this is magnitude of v. All right, so if we do the dot product with v with itself, we're going to get negative 3 sine t, 3 cosine t, and 2t. Negative 3 sine t, cosine t, for my 3, and my 2t. Okay, so doing the dot product, multiply like components and add, so negative 3 times negative 3 is a positive sine 9 sine squared t, plus 3 times 3 is 9 cosine squared t, plus, and then 2t times 2t is going to give me 4t squared. Okay. You may notice here, this has a 9 in common, so this is 9 times sine squared t plus cosine squared t, but this is equal to 1 identically, so this then simplifies to 9 plus 4t squared. And remember, this is under the square root, so the actual speed then is equal to the positive. We'll take the positive square root of this. So this is the speed. Okay, so that's the speed at any time t. And then we wanted to know if the velocity is ever perpendicular to the acceleration. Okay. So if you recall, by definition, the orthogonality of two vectors is defined by the dot product. This is true if v dot a equals 0. So all I have to do is take the dot product of these two things and solve for t to find out if at any time those two things are ever 0. We have negative 3 sine t, 3 cosine t, and 2t, dotted with negative 3 cosine t, negative 3 sine t, and 2. Okay, and we're going to see if this thing equals 0. So, likewise before, we have negative 3 times negative 3, so that's going to be 9 sine t cosine t, minus, looks like we have 9 cosine t sine t, and then plus 2 times 2t is, oh, write that out, is 4t. This looks like that equals 0, so you're just left with 0 equals 4t, which implies then that only at t equals 0 are a perpendicular to v. Okay? All right, so we found the speed, and yes, they are perpendicular, but only at the time when we started our clock. Otherwise, they are not. Okay, I hope that was helpful, and I will see you in the next. All right, in this example, we want to look at solving example 3, which is proving this dot product for u and v, that proving the dot product rule for the potential for the words they're failing. Want to prove the dot product rule for these. Okay, so we're going to let u, we'll just do that it's 2 components, but the same is exactly true if we had more than one. And v is going to be v1, v2. So if you did 3 components, for example, the same exact analogy would hold. You just add another component. Okay, so we're going to prove that and recognize that we understand that v, both u and v are parameterized by t. In other words, they're functions of t. So in each of the components are as well. Okay. All right. So let's go ahead and carry this out. And notice the order of operations here. So we're going to carry out the dot product first. So u dot v is equal to, well, what is that? That is u1, u2 divided with v1, v2. So you can see why I'm limiting it to two components, but if we were going to carry this out, we would just extend it. It's very v looked funny. So maybe rewrite that. There we go. And also notice that these are functions of t as well. Okay, so we have here u1 v1 plus u2 v2. Okay, and then we had more components, we just consider it dot dot dot. Okay. All right, now that we have this, okay, we're going to then take the derivative of this. So d dt, this entire thing, u1 v1 plus u2 v2. Okay, and so using linearity of the derivative, we consider each of these individually. So d dt of u1 v1 plus d dt of u2 v2. Okay. And now, since these are just regular functions of one variable from Calc 1, we can use the product rule on each of these individually. There's nothing there. We already have proven that in a previous course. So it's going to be du det v1 plus also u1 dv1 dt. So now it's just a matter of bookkeeping. And then we get du2 dt v2 plus u2 u2 dv2 dv. My u's and my v's are looking so it still looks like a v. All right, that's a v. Okay, and now we're just going to combine like terms. So we'll move all of the u's together and all of the v's together based on their derivatives. Okay, so it looks like these two terms we will group together. And it looks like those two terms we would group together. And so you're going to do this similar thing if you had more components. So for example, if you had three of them, you would follow that same logic. And so what do we have? We have du1 dt plus, oh, sorry, I got my v1, plus my du2 dt v2. Okay, so that's those two, and plus, and then I have u1 dv1 over dt plus u2 dv2 over dt. Okay. And now I think the form will start to show out. Okay. What is this? Well, this is just it's like du, the vector, dt dotted with v, not v1, dotted with v. And what is this over here? Well, this looks like it's the vector u dotted with d, v, d, t. Okay. And so I hope you can see that if we extended this out, we would have similar. This part would just be longer, and this part. Okay. All right. I hope that was helpful, and I will see you in the next video. Right. In this example, we're going to consider the cross product of two vectors that are dependent upon v, or sorry, t, and then take the derivative and see how that corresponds. So to do this proof, we're going to look at the derivative of u cross v. Okay. And so this is equal to, by the definition of the derivative, the limit as h approaches 0 of u v plus h times v of t plus h minus u of t cross v of t all over h. Okay. Now this next part is going to feel a little like unmotivated or confusing, but I think you'll see why. once we kind of show the magic that results. And so we're going to take this value here, and we're going to add a u plus across. Sorry, we're going to add and subtract an extra term. Let me write it. Let me write it down. That may more sense. So we have a u of t cross v of t plus h minus u of t cross v of t plus h. So we're going to add and subtract this term to this quantity. And it may seem unmotivated as to why we're doing that, but I think you'll see how it allows us to simplify things, because remember, we're trying to show this. Okay. All right. So let's go ahead and take this term and throw it into our limit. So I'm just going to write it around. We have u of t plus h plus v of t plus h plus minus u of t cross v of t. Okay, so I'm just adding those in, subtracting. I'm ignoring the limit and the h for now, just so you can kind of see the general form here. All right, and so if I do that, then by the property of the cross product, I can simplify this and regroup some things. So the u of t, so this quantity here and this quantity, I'm going to group together with the limit, and that's going to go with that term there. Okay, so I think it'll be easiest to see. I'll just write it out. You can see. So the limit as h goes to 0 of u of t plus h as, sorry, minus u of t over h. That's being crossed with the limit as h goes to 0 of v of t plus h. And we're going to add to that then the limit as h goes to 0 of u of t cross the limit as h goes to 0 of v of t h minus v of t, all divided by h. So from this line, you can see why we added and subtracted this extra term. Yeah. Yeah, so you can see there why we added and subtracted that extra term. It allows us then to separate using that property of the cross products. It allows us to separate into the sum of the two individual terms. And now I think you can see quite quickly how this turns into log. So this right here is the definition of u prime. Okay, so this is the definition of du dt. And that's going to be crossed then with that, and the limit just turns into b of t plus, and then here, this is in the limit of t, it's just literally going to be u of t cross, and then this becomes a derivative of v of t. Okay, and this is what we were trying to show. So the trick to this one, it's a little bit tricky. If you didn't see this, or if you didn't know to add and subtract these terms, notice that we're adding subtracting 0, but this then allows us to break it up into the two quantities that we need using the limits and the property of cross products to separate them individually. And then in the limit, as h goes to 0, we recover the v and the u and use the definitions there. Okay. All right. I hope it was helpful, and I'll see you in the next video.